So, a very good morning, participants. So, welcome to Kongunadu College of Engineering and Technology. So, today, day 3, AICT sponsored 2 weeks online challenges in VLSI mixed signal processing for fourth industrial revolution, phase 2. Uh, so, today, our resource person, Mr. LV Kedarnath, Field Application Engineer, Central Technologies, Bangalore. Welcoming, sir.
Thank you, sir.
So the today topic going to session small introduction about our today resource person, our student Pranita, to give our small introduction about today resource person. Thank you.
Good morning to one and all gathered here. It's my immense pleasure to welcome our today's resource person, Mr. LV Kedarnath, Field. It is a sign of your heart says welcome. The love will come pouring from everywhere. He is a field application engineer at AICTE Technologies based out of Bangalore, India. He is responsible for construction for customer across India in all activities supporting Verilog and physical design flow work groups. He carries 2 years of training experience with the core expertise in physical design and verification. He controlled in developing learning solution in the scope of RTL design, physical design, and more as subject matter expert. He holds B.Tech in Electronics and Communication stream from MLR Institute of Technology, Hyderabad. I would like to hand over this session to our today's resource person, Mr. LV Kedarnath. Please, sir.
Yeah, thank you, ma'am. Thank you. So, is my screen is visible, ma'am?
Yes, sir. Visible, sir.
Yeah, thank you, sir. Yeah, good morning to everyone. Today's we are going to discuss with about memory cell. So how that memory cell functionality can be built and till what are the steps involved in your semi-custom IC design flow. So those are the things today which we are going to discuss about. So and today's session agenda is what is the overview of semi-custom IC design and what is the importance of RTL code and synthesis with DFT and without DFT and design for testability along with that the physical implementation of your design. So that is your today's session agenda, what we are going to take care. And when it comes to the first thing, what is your semi-custom IC design flow? So semi-custom IC design flow, or we can call it as ASIC design flow. So the first thing, whatever may be the design you are working, you will be taking care of your specifications part. So on which technology node you are doing the design and under which conditions you are considering. So all those parameters you will be considering as specifications. So once that specifications has been done, then we'll be going with the RTL coding file. So where we are using the register transfer logic coding. So we are having the different formats of coding also, like TTL logic it is available, and RTL logic is available, or I2C logic it is available. Why only the RTL logic we are considering when we are going with the VLSI design flow? So RTL logic is basically representing a register transfer logic. So register in the sense storing a data and transferring the logic whenever it is required. So that's why most probably we are using the register transfer logic for writing your RTL code and for performing your design considerations and all those things. So when it comes to your RTL coding, we are having the different formats of RTL coding again. So we are having Verilog format of RTL code, VHDL format of RTL code, system Verilog format of RTL coding. So you are having different formats of RTL code which can be used for writing the logic. So if we are, so it depends upon the individual on which format he will be able to write. So one person may be completely familiar with Verilog, and the other person may be familiar with VHDL, and the other person may be familiar with system Verilog also. So it depends upon the individual user on which format he is comfortable in writing the RTL code, and he can choose that particular format for writing the RTL code. So whatever the format you are writing, either in Verilog, VHDL or System Verilog, so all these formats are supported by your Cadence EDA tools. So that is where your RTL coding. So when it comes to your Verilog or when it comes to VHDL, we are having the different formats of syntaxes again for writing that RTL code and all. So that is where, according to that choosing of format, user has to write the RTL logic and he need to save that particular files. So that is where your RTL coding. So once after writing the RTL code, then you will be moving to your functional simulation stage. So in this functional simulation stage, you will be verifying the functionality. So whatever the RTL logic you have written, so that RTL logic will be verified in your functional simulation stage. So when it comes to your functional simulation, we are having the different steps involved in your functional simulation. The first one is your compilation. So where it will be checking your syntax checking. So whatever the RTL logic you have written, according to that, it will be checking the syntax checking, and it will be analyzing the source code and if there are any errors in your syntaxes. So all those things will be checked under your compilation stage. So that is your compilation. And the next step is your elaboration. So in this elaboration stage, so the tool will be considering what are the modules available in the design, and it will be checking what is the high top module or hierarchical module which is in the format of RTL code, and it will check your connectivity issues, and along with that it will prepare the results for your simulation. So that is where your elaboration. So if your compilation is not done successfully, then it is not possible to move to your elaboration stage, because you are having the syntax error at your compilation stage. So if you are having any syntax error at your compilation stage, so that cannot be proceeded to your elaboration, because without the syntax error, if you are having the syntax error, automatically the logic will be missing. So that's why once the compilation is done successfully, then only it is possible to move to your elaboration stage. If not, you need to go back to your RTL code, make the modifications, and then you need to save the file, and then you need to go back to your compilation once again, and then move for your elaboration. So if elaboration, when it comes to your elaboration stage, so it will be checking whatever the logical connectivities you have made, and according to that, it will be checking what are the modules available, and among the list of modules, which is the hierarchical module, so which is the top module. So all those things will be considered at your elaboration stage, and it will be checking the functionality also. So that is your second step in your functional simulation stage. And the third one is your simulation. So depending upon your inputs or depending upon your input specified, so according to that, your outputs will be generated as per your logic. So that is where your simulation stage will be taken care. So if elaboration is done, is not done successfully, so simulation will be is also not possible. If elaboration is done successfully, then only it is possible to move to your simulation stage, and according to that input specified by the user, he'll be getting the expected outputs. So that is where your simulation stage. So after generation of your outputs, you can rectify or you can verify that outputs whether whatever the input specified, according to that your logic is performing or not. So if that particular logic is not performing, so automatically your logic will be missing whatever we have written in the RTL format. So that things we need to take in care at your simulation stage. So for doing that functional simulation, we are going to use a Cadence tool, that is Incisive. So Incisive is the tool name for checking your functional simulation. So where it will take care of your compilation stage, elaboration stage, and then your simulation stage. So that is your functional simulation. So once after verifying the results, so if that result is satisfied, then you will be going for your synthesis stage. So where you will be converting your RTL code into a gate level netlist file. So whatever the RTL code we have written, so that is the user can be understandable. So to get your machine understandable language, we'll be converting that RTL code into a gate level netlist file by using your technology node. So technology node is basically representing under which nanometer of your design, under which technology you are working on your design. So either it is 180 nanometer or 90 nanometer or 45 nanometer or below 45 nanometer. So it depends upon the user again. So under which technology is working, according to that technology node, your logic will be mapped with your gate level netlist file. So that is where your synthesis process has been taken care. So which is always a three-step process. The first one is your translation or generic process. So at this translation stage, so whatever the basic RTL logic you have taken, so that will be converted into a basic logic gates. So that is your translation process which will be taken care under your synthesis. And the second one is your mapping. So whatever the logic it has been converted into basic logic gates, so that basic logic gates will be mapped with your respective technology node, and that respective technology node will be giving you a mapping process. So depending upon the logic which the tool can be understandable or the machine language, so that will be converted by using the respective technology node under your mapping step. So that is your mapping process. And the last one is your simulation. And the last one is your optimization. So depending upon the optimization, so depending upon the logic, so if the logic is able to modify or if the logic is able to optimize the design, so at the time you can go for optimizing process. So that is a three-step process under your synthesis, translation, mapping, and then your optimization process. So which is a three-step process of your synthesis stage. So this is how your synthesis process will be happening. So the first step, whatever the RTL code we have written, so under your translation process, that will be converted into your Boolean expressions or your basic logic gates. So that basic logic gates will be moved into your optimization and mapping process, which will be converted into your respective technology node. So whenever we are able to see in your translation process, so it is able to see only a two input gate. Along with that, one more input you are getting from the other gate. So at the time, so in your mapping process and your optimization process, so that will be converted into a three input AND gate. So that is how your optimization and the mapping process will be done, the respective technology node of your design. And these are the input files for your synthesis. So for performing your synthesis, we are going to use the tool Genus. So Genus is the tool which we are using to perform the synthesis process. So the input files will be your RTL code. So the input files will be your RTL code. Either you have written in .v or .vsdl or .sv. So .sv is the advanced version of your Verilog. So any of the format will be taken as one of the input file for your synthesis. The other input file is your SDC. So .sdc represents your synopsis design constraints, where you will be specifying your clock information. Along with that, you will be specifying your input and output delay information of your design. So if you are working with the combinational logic, your SDC file is optional. If you are working with the sequential logic, your SDC file is a mandatory thing, because your sequential blocks will place a major role on the clock signal itself. So depending upon the clock signal, it will be defining your logic. So at that particular point of time, your SDC file is a mandatory thing. So where it will be having your clock information, and along with that, it will be having your input and output delay information also. So SDC reference, synopsis design constraints. So whatever the SDC we are giving as an input for your synthesis tool, that is your chip level SDC or top level SDC file. So where for your entire chip, it will be taken care as one of the common SDC file by using your synopsis design constraints. So these parameters will be specified by your at your specification stage itself. So where you will be defining what is your clock time period of your clock signal, what is the time period of your clock signal, and what is the rise time of your clock signal, and along with that, what is the fall time of your clock signal. So all those parameters will be taken care under your SDC file. So after that, that is your second input file. And the third input file is your .lib and .left file. So .lib libraries, so we are calling it as a library file. So .lib represents your liberty file, which is having your timing information of your logical cells. So whatever the timing information it is available for your design, so according to that, the timing information will be generated for you from your .lib files itself. So .lib is basically representing a liberty file, and the other file is your .left file, which we are calling it as a library exchange format file, which is having your cell information. So what is the cell height, what is the cell width, and what are the metal layers used for that particular cell. So all that related information will be available from your left file itself. So a combination of .lib and .left, we are calling it as a library files. So Liberty and library exchange format file. And Liberty file will be having your timing information, and .left file will be having your cell information. So those are the three input files for your synthesis tool, for your synthesis. And then you will be performing your translation by using the syn generic option, and then mapping process by using synmap, and then your optimization process. So after performing your synthesis, then you will be getting your gate level netlist file as of your output, and then you will be getting your block level SDC file, which is according to a tool understandable language. So whatever the SDC we are giving, that is user understandable, and whatever the tool it is generated the SDC file, that is your block level SDC file. So which is basically representing your individual block. So how we can tell that what is your individual block? So whenever you are taking a mobile fabrication, so for building your mobile chip, what are the things required? So to perform your mobile application or any mobile functionality, so what are the major things we will be looking? So the first thing, camera features. What is the camera feature? Camera features are available, and what is the RAM, and what is the storage capacity, memory, and what are the battery backup, and so those are all the rest of parameters which will be taking care when you are trying to buy a new mobile. So similar way, that is your top level design. Your mobile is your top level design. But when it comes to your internal blocks, so there are different blocks like camera block and a memory block and a RAM block. So similarly, your battery block. So there are all the different sub blocks available in your top module. So mobile is your top module. When it comes to your sub module, your camera, memory, RAM, and your battery. So these are all the sub blocks in your design. So for that sub blocks, you'll be working on any one of the block, either in camera block, or you'll be working in memory block, or you'll be working in a battery block. So for that particular block, so whatever the SDC it is generated from the synthesis tool, so that is your block level SDC file. So we'll be calling it as a block level SDC file, which is only dedicated to your individual block. And whatever the input we are giving, that is for your entire chip. And whatever you are getting as an output, that is only specifically for your individual block only. So that is your block level SDC file as one of the output from your synthesis. And then you will be getting your log file and the reports. So you can get what is your estimated area report, what is your estimated timing report, and what is your estimated power report. So all those reports can be seen after performing your synthesis. And you can see what is how your .lib format will be available. So this is a sample Liberty file of your .lib. So how it will be available. So all those parameters you can able to see. So along with that, you can see what is your operating conditions of your Liberty file. So process is 1 and voltage is 0.9 and the temperature is 125 degrees. So operating conditions are slow. So whenever your library files have been characterized, so your library files are characterized with a different PVT corners. So PVT reference process voltage and temperature. So depending upon that PVT values, your libraries have been characterized like slow.lib, fast.lib, and typical.lib. And this is your cell of your D flip-flop cell, and you can see what is the area, and you can see what is the direction of your pin, and what is the capacitance, and what is the internal power, and what is the timing information. So each and every timing information of that particular cell will be available in your .lib file. And when it comes to your left file, which is having your cell information, so what is the cell height and what is the cell width, and what are the metal layers used for building that particular cell. So all every information from of your design of your left file will be available in your left file, library exchange format file. A combination of your .lib and .left, we are calling it as a library files. And then your RTL file as an input, and these are the SDC constraints. So synopsis design constraints, where you will be defining your what are your clock signals and what is your rise time and fall time of your clock signals, and along with that, what is the delay between your signals and the clock, and you can define your what is your output capacitance and input capacitance and all. So all those parameters you can specify in your SDC file. So synopsis design constraints file, and this is how your synthesis flow will be happening. So the first thing will be loading your library files as your .lib and .lab files, and then you will be loading your RTL code. So either .v or .vsd file, whatever the format of your RTL code you have written. So according to that, you will be loading your .v and .lab files, and then you will be elaborating the design. So elaboration basically represents checking the functionality of the design, and then we will be loading your constraints file, your top level constraints file, synopsis design constraints file, which is having your clock and clock information and your delay information between your signals and the clock, and then synthesize to generic, where it will be performing your translation process, and then synthesize the gates and optimize the netlist of performing your mapping and optimization process, and then generation of your outputs. So this is your synthesis process without using the DFT. And for that, we are going to use the tool Genus. So Genus is the tool, and this is how the script will be written for your synthesis tool. And the next one is your DFT. So after performing your synthesis process, then you will be going for your timing simulation, checking the timing reports of your design, what is the timing, and so all that report will be timing analysis you will be performing, and then you will be checking your timing simulation, what is the estimated timing it is taking to transfer the signals and to perform the logic. So all those parameters you will be checking under your timing simulation, and then you will be going for your DFT, so design for testability, where you will be checking the design by including some parameters like automatic test pattern generation and the creation of your fault models and the building of your fault models. So those things will be performed under your DFT. And for doing that DFT, we are going to use a Cadence tool, that is Modus. So Modus is a Cadence EDA tool which will be used for performing the design for testability. So that is your DFT. So that we'll discuss in detail while we are going with the DFT procedure. And the next one is your physical implementation. So the physical implementation, which involves in your 5 stages: the floor planning, power planning, placement, CTS, and then routing. And the CTS is optional when you are working with your combinational logic, and CTS is mandatory when you are working with the sequential design. And for doing that physical implementation, we are going to use the tool Innovus. For the Innovus tool will be to perform your physical implementation of your design. So that is your semi-custom IC design flow. So while we are going with the physical implementation, we will discuss in detail what is the floor planning, what happens in the floor planning, and why we need to go with the floor planning. So all details we will discuss in detail when we are going with your physical implementation system. So now you can invoke now you can write your RTL code of your memory design, and you will perform the process in the semi-custom IC design flow. So one after one, first we'll take a functional simulation, then we'll be going with the synthesis, and then we'll go with the DFT, and then we'll be going with your physical implementation of your design. So that we'll be seeing one of one in detail. So before going to your design, so first here, so always the Cadence tool will be working in your RHEL Enterprise Linux, Red Hat Enterprise Linux operating system. So these are the tools only supported in your RHEL, and even if you try to do it in Windows, it is not possible. So that is your RHEL operating system, which we are going to use to work on the Cadence tools.
Sir, hello, sir.
On your terminal. Yes, sir. Hello. Hello.
Sorry, voice is not clear, sir. Some disturbance is there.
Okay. Sure, sir. Yeah. Thank you, sir, for reminding back. So you can create your folder from your terminal. So you can create your folder. So already I have created a folder for memory. So for creating that, even I'll show you how to create that particular folder also. So you can select, suppose if you are trying to create a new folder, so you can right click on your screen and you can find the option open terminal, and you can find the option open terminal. So it will be opening a new terminal window.
Sir, no sir. Sorry sir.
So it will be opening your new terminal window.
Sir, Kedarnath sir.
Hello. Yes, sir.
Sir, sir, still there a disturbance is noise, sir.
Okay, okay. So now is it clear, sir?
Now, yes, sir, some noise
Hello?
is there, sir. Some noise is there, sir. Voice not audible.
Okay,
Sir.
okay. Yeah, you can right click and open in terminal option. So that will be opening a terminal window. So in that terminal window, so you can use mkdir command for creating
Sorry,
a
sir,
directory.
sir. Sorry, sir. So again, a voice not
Yes,
clear,
sir.
sir.
Okay, okay. Just a minute, sir. I'll just reconnect it, sir. Just a minute.
Yes, sir. Yes, sir. Yes, sir.
Hello. So now is it audible, sir?
Yes, sir. Yes, sir.
Hello.
Yes, sir. Audible, sir.
Sir, is it audible, sir, now?
Yes, sir. Audible, sir.
Hello.
Sir, it's audible, sir.
Sir, is it audible?
Yes, sir. Audible, sir.
Sir, is it audible, sir?
Yes, sir. Audible, sir.
Hello. Hello. Yeah. So you can create your directory by using the mkdir command. So mkdir space whatever the folder name you want to specify. So you can specify that folder name. So as of now I'm just creating a folder with test mkdir test, and then I'm entering into that. So and then I'm creating a folder I'm into my particular directory by using the cd command. So cd represents your current directory. So cd represents your current directory. So cd underscore test. So cd represents your current directory. So cd underscore test. we are using. And you can enter into your particular directory. So already I have created a folder with my memory. So I'm just entering into my memory folder. So cd space memory. So I have entered into my memory folder. So after entering into your memory folder, you can initialize your C shell scripting. So whenever you are working in Linux operating system, so for Linux operating system, we'll be having two scripting languages. So two shell scripting languages. One is your C shell scripting, and the other one is your Bash scripting language. So always the Cadence tools will be working in C shell scripting language. So that's why you can use the command CSH. So CSH reference initializing the C shell scripting language. So CSH reference initializing the C shell scripting language and enter. So we are initializing the C shell scripting and then we are sourcing the CSHRC file. So in that CSHRC file, you'll be having your tool data available. So what are the tools available and where is the tool is located? And all that information will be available in your CSHRC file. So that's why we are calling the CSHRC file as C shell scripting run command file, which is having your tool data available. So for that, you can source your CSHRC file, source space /home, source space /home /install /CSHRC, source space /home /install /CSHRC. So it will invoke your Cadence toolsuite. It will display a message that welcomes to Cadence toolsuite. Suppose without initializing the C shell scripting, so if you try to load your CSHRC file, so it will show you the error message. So it will show you the error message without sourcing your CSHRC file. So now we need to create your RTL code. For that, we are going to use the graphical editor. So for that, we are going to use the option gedit. So gedit represents graphical editor window. So how we are using your WordPad and Notepad in the Windows operating system. Similar way, gedit is one of the editor for writing any text document or for writing any codes in your Linux operating system. So gedit represents graphical editor and I am defining my file name. So memory.v is my file name. So gedit reference graphical editor space my file name with .v extension. So .v reference Verilog file. If you are writing in VHDL, you can give the extension .vhd. If you are writing in system Verilog, you can use .sv. So memory.v. So it will open you a blank document. And so as of I have already written my RTL code, so that's why automatically it will display my RTL code. So generally it will display a blank document. So you need to write your RTL code in your blank document file. So first I'm creating a module. So first I'm creating a module and I'm naming that module name as memory and I'm declaring my port list. So in the braces, I'm declaring my port list as clock. So clock signal is one of my input and WE write enable pin is one of my input and load address input D in and D out. So these are the list of pins available. These are the list of pins considering for my memory design. So among these list of pins, I am declaring what are my input pins and along with that I am declaring what are my output pins for my design. So for that input, so input, what are the inputs you are considering? You can declare the input pin name from the port list available. So clock, WE, write enable and load. So these are my input pins for my memory design and along with that 4-bit of address pin and 4-bit of D input. So these are all the input pins for my design, memory design, and my 4-bit output D out is my output pin. So I'm taking with 16-bit address memory. So that's why 3 of 0 of memory to 16-bit. and I am declaring my functionality. I have declared my what are my input pins and output pins of my design, and I am declaring what are the logics available in my design. So that is my uh, logic of my loading of my inputs and output pins of my design. And then I am declaring my logic by using the always statement. So always so for building my logic. So always at the rate passage clock. So always at the rate passage clock. So whenever my clock is positive, I am instructing to perform my logic. So that is the condition which I have taken in my always statement. So whenever my clock is positive, it should perform my whenever my clock is positive, it should perform my logic. So that is the condition which I have taken for my design. And then I'm using the begin and end statements for building my logic. So in that begin and statements, I'm using my if else statement for building the logic. So I'm stating my if condition. So whenever my if condition of load is equal to 0, so at the time whenever my load value is 0, so at the time my memory should be empty. So whenever my load value is 0, my memory address bit should be 0, because whenever my load is 0, automatically my data also will be 0. So that is the condition which I have specified in my if statement. And then I'm using my if else statement. So depending upon my write enable. So depending upon my write enable pin. So whenever my write enable pin is high, it should perform whatever my input data is available. So the same input data should be transferred to my memory pin. So whenever my write enable pin is high, so whatever my D input data is available, the same input it should transfer to my memory bin. So that is the condition which I am using in my else if statement. And in my else statement, so whenever your write enable is 0, so whatever the data available from memory, that will be passing to your D out pin. So that will be passing to your D out pin. So that is the condition which I have considered in my else statement of my second else statement of my design. And then I have begin the statement. So I'm ending my statement. So I have used the begin and statements for building my logic. So I have created a module. Now I'm ending my module by using the command end module. So after writing the RTL code, you can save the file. So after writing the RTL code, you can save the file, or you can use Control plus yes, or you can use Control S for saving the file. And after saving the file, you can close it. So after saving the file, you can close it. And similar way, you can write your test bench code also for writing your input values. So for writing your the input values of your input pins. So I'm declaring my memory test for my test bench module, and I have created with the module as memory test bench. So I'm created my module with the memory test bench of my test bench logic, where I can define my input signals, and along with that for the generated outputs. So and then I'm using whenever you are writing any test bench code, so in your test bench, all the inputs we are calling it as a register, as a temporary storage value, and your outputs will be declaring it as a wire option. So that is where we are declaring your inputs as reg and your outputs as wire. So reg, clock, WE, and load. Along with that, 4 bit of address and 4 bit of D input, and my output pin has 4 bit of D out. And I am calling my top module name by using the instantiation method. And I am calling my top module name by using the instantiation method. So memory is my top module name. So I'm calling with my memory, and then I'm declaring my UUT. So UUT represents unit under test. So whenever you are going with the instantiation process, we are having two ways of instantiation. One is DUT, and the other one is UUT design under test and unit under test. So we are declaring your top module as memory, and we are going with unit under test option, and we are declaring your port list, whatever the pins available. So we are declaring that particular pin names in your port list. And then we are using the begin end statements, and then we are using the initial begin end statements to declare your input and out input values of your design. So first I have declared my clock value as 0. So first I have declared my clock value as 0, and then I have declared my write enable pin as 0 initially. Initially I have declared my write enable pin as 0, and after 10 nanoseconds of time I'm declaring my write enable pin as 1, and after 10 nanoseconds I'm declaring my load value to 0, and after 10 I'm declaring my load value as 1, and after 20 nanoseconds I'm declaring my input along with my address bit value also. So 4 bit of address, and along with that 4 bit of D input pin I am declaring. So for every 20 nanoseconds of time I'm changing my address bit value, and along with that my D input pin value. So with respect to that write enable pin, my data will be stored in my particular output window as D out. So similar way, whenever your D out W is 0, so according to that your address will be loading. So that is the condition which you have mentioned in your test bench module by declaring the inputs of your design. And then we are stopping at 2000 nanoseconds of your time. We are stopping your simulation. For that we are using the system task function as $finish. So at 2000 nanoseconds, we are stopping your simulations. For that, we are using the system task function $finish and semicolon. And then we have declared your input as end. We have used a begin statement. So that's why we are ending that statement by using the end option. And then we are again getting back to your always block. So for every 10 nanoseconds of time, we are changing your clock signal. So if your initial clock is 0, and after 10 nanoseconds, your clock will be getting high. And after 10 nanoseconds, again, your clock will be getting 0. So we are using the always statement. For every 10 nanoseconds, your clock signal should be changing. So that is the condition which you mention your always block statement. And then we are once again using the initial begin for displaying of your values in your terminal window. So we are declaring your display values of your respective input and output pins. And for monitoring the values, we are using the $monitor option. And for displaying the values, we are using the $display option for seeing of your input and output signals in your design. And then we have begin the statement, so we are ending that statement, and we are closing the module. So we have created a module, so and then we are closing our module by using the end module option. So after that you can save the file, and you can close it. You can save the file and then you can close it. So after closing your RTL code, now you need to invoke your incisive tool. So for invoking your incisive tool, you can use the command nc-launch. So you can use the command nc-launch. So nc-launch is the tool from your incisive. For invoking your incisive tool, you can use the command nc-launch space -u. So -u is the switch option for when you are working with any new designs. You should need to create your cds.lib file. So for creating that cds.lib file, we are using the switch option -u. So nc-launch space -u. So it will open you a nc-launch window. So where you can see your multiple step and single step option. So multiple step, which happens one after one process like compilation, elaboration, and then simulation. And if you choose the single step option, all the three processes will be run at a single time. So the compilation, elaboration, and then simulation will be run at a single time, so that you cannot observe what will happen at your compilation stage, and what will happen at your elaboration stage and what will happen at your simulation stage. So that's why you can select your multiple step option. So you can select your multiple step option, and it will show you for which it need to create your cds.lib file, and it will show you for which it need to create your cds.lib file. So cds.lib file reference cadence design system dot library. So cds.lib file reference cadence design system dot library. So that cds.lib file will be having your design information. So that cds.lib file will be storing your design information. So that's why you can click on create cds.lib file. So you can click on create cds.lib file. So it will show you how to create a cds.lib file. So it will show you how to create a cds.lib file. So the default file name will be cds.lib. So if you want to rename the file, you can rename it with the extension .lib only. So if you want to rename the file, you can rename the file with .lib extension only. So I'm going with the same default name as cds.lib and clicking on save option. And clicking on save option. So it will show you in which format file, and it will show you in which format we need to create your cds.lib file. So you can see the first option, include default libraries. So you can see the first option, include default libraries. So include default libraries. So include default libraries reference your VHDL format. So include default libraries reference. So your VHDL format. And the second one, include IEEE pure libraries. If you are having the IEEE format of VHDL library, you can use your VHDL of IEEE format. You can choose the second option. And the third one, do not include any libraries of Verilog design. So if you have written your RTL code in the Verilog format, you can choose the third option. If you have written in system Verilog also, you can choose the third option. If you have written in VHDL, so depending upon the VHDL format, you need to choose either first option or second option. If you have written normal standard of VHDL, you can choose the first one. If you have written IEEE format of VHDL, you can choose the second option. And you can choose the third option from the list of options available. Do not include any libraries. And you can choose the third option, do not include any libraries. And you can click on OK. And once again, you can click on OK. So it will open you a NC Launch main window. So it will open you a NC Launch main window. So where on the left hand side, you can see your directory. So where on the left hand side, you can see your directory. And on the right hand side, you can see worklib and snapshot. So under directory, you can see your .v files are available. So under your directory, you can see your .v files are available. And the bottom window will be your log window of your incisive tool. And the bottom window will be your log window of your NC Launch tool. So you can select your top module from the list of files available on the left hand side. So you can select your .v file of top module. So my top module is memory.v. So that's why I'm selecting my memory.v file. So that's why I'm selecting my memory.v file. And you can go to tools. So you can go to tools and you can see the option VHDL compiler or Verilog compiler. So the first step in your functional simulation is your compilation process. So at this compilation stage, the syntax checking will be done under which format of RTL code has been written. So if you have written in Verilog, you can choose Verilog compiler. If you have written in VHDL, you can choose VHDL compiler. So depending upon on which you have written, so according to that, the Verilog compiler will be listed. So you can select your Verilog compiler and you can, so that it will open you a compile Verilog window. So along with that, it will show you a file path. So where the .v file path has been loaded. So you can see under file option, you can see the path of your .v file. So in which file it is, in which path it is there, it will show you that particular path along with your file name. And you can click on OK. you can click on OK. So with the default settings, so it will run your compilation process. So it will run your compilation process. So if there is any error in your compilation stage, it will be displaying at the bottom side of your window. It will be displaying at your bottom side of your window. Similar way, you can select your test bench module. So similar way, you can select your test bench module, and similar way, you can select your test bench module, and you can go for tools, and you can go for tools. Can go for tools. Similar way, you can select your test bench module, and you can go for tools, Verilog compiler. You can go for tools, Verilog compiler, and then go for compilation, and then go for compilation. So you can select your test bench module under your list of files available, and you can go to tools, select your compiler, either it is Verilog or VHDL compiler, and click on default option. So it will open you a compile Verilog window. So where you can check the path of file available, and you can go with the default settings, and you can click on OK. So that if there is any errors in your design, so if there is any error or any warning messages in your RTL code, it will display that particular error message. So it will display that particular error message. So it is particular. So here I am able to see a message that expecting a semicolon is my syntax which I'm missing, expecting a semicolon. Along with the you are seeing. So at line 30, it is missing my semicolon. So you can go back to your RTL code, you can select the file, and you can see the browser option. And you can see the browser as edit option. So you can click on that edit. So it will open you a particular Verilog file. And at line number 30, it is having the error. So at the bottom right corner, you can see what is your line number and what is your column number. So at my line number 30, it is having my error. So after finishing my always statement, I forgot to give my semicolon. So I'm giving specifying my semicolon, and once again my file, once again saving my file and closing my file. Now we'll come back to your NC launch window. So once again, you can select your test bench module. You can go to tools, Verilog compiler. So you can go to tools, Verilog compiler, and from Verilog compiler window, you can check your file path from your compile Verilog window. Select your file path and click on OK. Even if it is the while error message or any warning message, it will display you at the bottom side of your window. So it will display you at the bottom side of the window. So the compilation is done successfully. So if the compilation is done successfully, your work list will be created. So the compilation is done successfully, work clips will be created. If not, the work clip will not be created for the file. So if the compilation is not done successfully, the work clips will not be created for the respective .v files. So under work clip, you can expand your work clip directory from the right side of your screen. So under work clip, you can select your top module. So under work clip, you can select your top module, and you can go to tools. So that is your compilation process of compiling of your .v files. If the compilation is done successfully, so under worklib, you can able to see your module names. So that module names will be forwarded to your elaboration. And that module name will be forwarded to your elaboration tool. Clip your top module name. So under worklib, select your top module and go to tools. Go to and select elaborator. go to tools and select elaborate. So it will open you a elaborator window. So it will open you a elaborator window. Any with the things and no, so that will run your so the elaboration tool. So that will run your elaboration of your design. So you can tools select the elaboration is done successfully, so that the shots will be created. So if the elaboration is done successfully, so that the snapshot will be created. So if the elaboration is not done successfully, so that the snapshot will not be created. So under snapshot, you expand your snapshot so that you can see whether your worklib has been created or not. For that module, you can see whether that worklib has been created or not. So that is your elaboration stage of your top module of your design. So similar way, you can do it for your worklib. Select your test module name and go to tools. So under worklib, select your test module name. So go to tools and choose the option elaborator and go to tools, choose the option elaborator. So it will open you a elaborate window. So under that elaborate window, so go with the default settings and click on OK. And go with the default settings and click on OK. So that elaboration also will be done for your test module. So if the elaboration successfully, so under your snapshots, the test module library also will be created. So under your snapshots, the test module worklib also will be created if your elaboration is done successfully for all the modules. So if you are having the submodules in your top module, even you need to compile and elaborate those modules also. So even if you are having the submodules in your design, so we need to compile and elaborate the submodules also. So that is your elaboration stage. So if the elaboration is done successfully, so then snapshots will be created. So under snapshots, select your test module. So under snapshots, select your test module. So under snapshots, select your test module. Suppose if you have not written your test bench, you can select your top module only. You can give the manual inputs for your design. You can give the manual inputs for your design. So under snapshots, select your test module and go to tools and choose the option simulator. And go to tools and choose the option simulator. So under snapshots, select the test module, go to tools and select simulator option. So it will open you a simulate window. So go with the default settings. So you can go with the default settings. Just click on OK. Can go with the default settings. Just click on OK. So it will open you a SimVision window. So it will open you a SimVision window where it can run your simulations and generate your waveforms. So it will open you a SimVision window. So it will go to a simulator window and generate your waveforms. So after opening your SimVision window, so it will open you a design browser window. So it will open you a design browser window. So under the design browser window, you can see your test module name. So under your design browser window on the left hand side, you can see your test module name, and on the right side, you can see the objects option. On the left hand side, you can see your design browser, and on the right hand side, you can see objects window. So you can select your test module name. You can select your test module name from your design browser window. Automatically on the right hand side, you can see your objects. Automatically on the right hand side, you can see your objects. So after selecting your test module, right click and you can choose the option send to waveform window. And you can choose the option send to waveform window. So it will take your signals to your waveform window. So it will take your signals to your waveform window, and you can run the simulation. So you can go to simulation and choose run option, or you can use the shortcut key letter F2, or you can use the shortcut key letter F2 for running your simulations. So it will run your simulations. So according to that, you will be getting your outputs. So according to that, you will be getting your output signals depending upon the input signals, which whatever we have specified. So depending upon the input signal specified, so the outputs will be generated to your waveform window. So that is your waveforms of your respected design of your memory. So after this, you can come back, you can go through your waveforms, whether whatever the logic you have written, according to that logic, it is performing or not. So if it is not performing, go back to your RTL code, make the modifications, and once again, you need to perform your compilation, elaboration, and then simulation. So if these waveforms are satisfied, you can go to your synthesis process. And before going to your synthesis, design will be looking. So after writing your RTL code, how your RTL code will be represented in a pictorial format. For seeing that pictorial format, you can come back to your design browser window. You can come back to your design browser window, and you have already selected your module under your design browser. So you have already selected your module under your design browser. So you can select that design and right click. You can choose the option send to schematic tracer. So you can choose the option send to schematic tracer. So it will take you to a schematic tracer window. So where you can observe your pictorial representation of your design. So where you can observe your pictorial representation of your design. So this is a outer look of your black box representation. If you double click on that block, so it will open what are the internal blocks available. So if you double click on that particular block, it will open what are the internal blocks available for your design. So UUT is your top module, and these are all the sub modules which are available in your design. So you can double click on your top module so that you can see the some more internal structures of your design. So you can see how your top module has been also built. So along with that, you can see how your top module has been also built for your design. So this is the internal structure of your top module design. By using the schematic tracer, you can see the pictorial representation of your design also. So that is your functional simulation process. And the next one is your synthesis. So to perform your synthesis, you can close your incisive windows. So you can close all your NC launch windows except your terminal. So you can close all your NC launch windows except your terminal. So if it is asking to save the file, you can just click on yes so that you can save your simulation results. So that you can select you can close your NC launch windows. So after closing your NC launch windows, now you need to invoke your synthesis tool. So what is your synthesis tool? So your synthesis tool name is Genus. So before invoking your synthesis tool, we'll try to have a look how your library file will be looking, and along with that how your left file will be looking. So to see that left file and lib file, so you can minimize your terminal window. So you can minimize your terminal window. You can click on home from your screen visible, and you can select other locations, and you can select other locations. From other locations, you can find computer. So from other locations, you can find computer. So from computer, you can once again select home. So from computer, you can select once again home. So in home, you can select install folder, because install is the Cadence tool set of files available with your tool data. So in install, you can find Foundry folder. So you can open Foundry. So you can open Foundry. So in Foundry, you are working with digital. So you can select digital. So in digital, you are having a different technology nodes available, like 45 nanometer, 90 nanometer, and 180 nanometer. So you can open your 90 nanometer. So in 90 nanometer, you are having the dig. So you can open dig. So in dig, you are having your lib folder. So in dig, you are having your lib folder. So you can open lib. So in lib, you can see a different files available like fast.lib, and along with that you can see slow.lib available, and along with that you can see a typical.lib also will be available. So depending upon the each library, your PVT corners will be varying. So depending upon the each library, your PVT corners will be varying. So slow.lib, fast.lib, and .lib. So all the PVT corners will be varying for the set of library. So I'll try to show you the difference in the PVT corners. So now I have opened my slow.lib file. So now I have opened my slow.lib file. So under that slow.lib file, you can see what are your operating conditions. So under that slow.lib file, you can see what are your operating conditions. So my operating conditions are for slow.lib libraries process is 1 and voltage is 0.9 and temperature is 125 degrees. My process is 1 and the voltage is 0.9 and temperature is 125 degrees centigrade. So that is my operating conditions for my slow.lib library. Similar way, we'll try to have a look at your fast.lib also. We'll try to see what are the PVT corners available for your fast.lib library. So your PVT corners for your fast.lib library is, so process is 1 and the voltage is 1.1 volts and the temperature is 0 degrees centigrade. So these are the different PVT values for your slow.lib and fast.lib. Whenever you go with typical.lib, your PVT corners will vary again. So similarly, you can go back to your lib folder and you can open your typical.lib file. So in that typical.lib file, you can find your PVT corners. So you can find your PVT corners. So you can find your PVT corners for your typical.lib also. So under this typical.lib also, you can see what are your PVT values for your typical.lib. So my operating conditions for typical.lib is process is 1 and process is 1 and the voltage is 1 and the temperature is 25 degrees. So that is my different PVT values for a different set of libraries. So that is your lib file information of your design. So now we'll invoke your genus tool. So we'll invoke your genus tool for performing your synthesis. So you can give the tool name as genus and enter. So you can specify the tool name as genus and so after loading the tool, first you need to load your library file information. So for that, you can use the command read underscore library. So for that, you can use the command read underscore lib and you can mention the path of your library file. And you can mention the path of your library file. So after invoking your genus tool, so you can use the command read underscore lib. You can use the command read underscore lib. You can use the command read underscore lib. So after invoking the Genus tool, you need to load your library files. For that, you can use the command read_lib space. So within double quotes, you need to mention the path of your library. So you need to mention your path of your library. So where my file path are available? So in your lib folder. So you can go back to your lib folder and you can select your slow.lib file. And you can select your slow.lib file. So right click and copy. So you can select the copy option so that the file path will be copied in your terminal window. So the file path will be copied in your window. So you can load it by using the read_lib command. So within double quotes, and you can right click and you can get the paste option. So if you click on paste, so the file path will be pasted and you can close within the double quotes. So you can load your library. So read_lib space /home /install/foundry /digital /90 nanometer/dig/lib and /slow.lib. So that is loading of your library file of your design. Yeah, just a minute. I'm just rechecking my tool. Just a minute. Yeah. So after invoking your genus tool, after invoking your genus tool, you need to load your library. So read underscore lib space, you need to copy the file, library file path. So within double quotes, you need to copy your library file path. So for that, you can choose /home /install /foundry. So foundry should be capital letters /digital /90 nanometer /dich /lib and slow.lib. So that is my library file name. And then you can load, that is your command for reading of your library files. So after reading of your library files, you will be getting what are the PVT coordinates loaded for your design. So you can see what is operating conditions for your slow.lib values. So you can see what are the slow.lib values of your design. And then you need to load your HDL file. So read underscore HDL. So your file name is memory.v. So we are loading that memory.v file. So after loading your HDL file, you need to elaborate. So to check the functionality of the design, you can use the command elaborate. So that is your third command while you are performing with your synthesis without using DFT. So elaborate to check the functionality of the design. And then you need to load a file constraint. So you need to load synopsis design constraints file. So first we are creating a clock signal. So create underscore clock space hyphen name. So I'm taking the clock signal name as CLK space hyphen period. So I'm taking the time period as 22 nanoseconds of time. And this is my external port connection. So get underscore ports of CLK. So for which of my clock signal I'm declaring as a port. So I'm declaring that particular clock signal name. And then we are setting the rise time for my clock signal. Set underscore clock underscore transition space hyphen rise. I'm mentioning my time period of my clock signal as 0.1 nanosecond. And then I'm declaring for my clocks. So for which clock signal I'm declaring my rise time. So I'm specifying that particular clock signal. So for that we are using the command set underscore clock underscore transition space rise at 0.1 nanoseconds get underscore clocks CLK. And then similar way I have taken my rise time. Similar way I'm taking the instead of rise I'm taking my fall time of my clock signal. So hyphen fall and enter. So setting the clock transition space hyphen fall with 0.1 nanoseconds get underscore clocks CLK. So setting the rise time and fall time of my clock signal. And the next one setting of your uncertainty time. Set underscore clock underscore uncertainty. Set underscore clock underscore uncertainty and setting some uncertainty time. So we are not sure that whether our clock signal will exactly move to your pin or not. So that's why we are setting some buffer time for our clock signal. So we are setting some buffer time for our clock signal as of uncertainty time. So now I have loaded all my inputs. So first input I have loaded my library file, and second input I have loaded my RTL file, and third input I have loaded my synopsis design constraints file. So giving of your specifying of your clock parameters. So setting the rise time of your clock signal, fall time of your clock signal, rise of your signal, and along that setting the uncertainty time of clock signal. So all the clock parameters are specified. And then now I'm performing my translation process. For that, you can use the command syn generic. So for that, you can use the command syn underscore generic to perform the translation process. Syn underscore generic to perform the translation process. So once after performing your translation, then you can use the command write underscore HDL. So under this translation process, your logic, whatever the RTL logic is available, so that RTL logic will be converted into a basic logic gates. To check whether it is converted or not, you can use the command write_HDL. Can use the command write_HDL to check whether the translation process is happened or not. So you can scroll it up to check whether your design is converted into logic gates or not. So our design is converted into the logic gates, so which you can see on the screen as NOT gate, OR gate, NAND, NOR. So each and every gate it is reflecting under my translation stage. So this is your translation process, conversion of your RTL logic into a basic logic gates. So after conversion of your RTL logic, then we'll be moving to your mapping process. So for doing that mapping process, you can use the command syn_map. Can use the command syn_map for the mapping process of your design. So syn_map. So it will run your mapping process. So the logic will be mapped with your respective technology node. The logic will be mapped with your respective technology node. So after mapping process has been done, you can see your mapping process by using the command write_HDL. So write_HDL to see how the mapping process has been done with your RTL logic. So these are the logic gates which has been used from your respective technology node, and the mapping process has been done for your design. So these are the logic gates. So whatever the dot it is reflecting. So suppose if I am considering the particular inverter cell. So for my inverter cell, so this is my technology representant mapping of inverter Excel, and G4800 is your basic logic gate, and dot A the pin name of your technology node. With the respect to that, the internal names are your basic logic gates input pin names. So that is your inverter logic. And similar way, always with dot representing of pin name will always reflect to your respective logical cell pin name, and the internal braces which you are able to the pin name, that is your basic logic gate pin name. So that is your mapping process. And the next one is optimization. So syn_ optimizing process of your design. So syn_opt, and then you can use the command write_HDL. So whether the optimization has been done or not. So even that optimization process will be done, and then you can see your estimated gate level netlist file. So I'm saving this gate level netlist file because I'm using the same file for my physical implementation. So I'm using it as memory_netlist.v. So memory_netlist.v. So that will save my netlist file of my design. And to save your SDC file, write_SDC, write_SDC. I'm using my .sdc file. So I'm saving my block level SDC file by using the write_SDC command. Write_SDC of memory.sdc, which will save your SDC file report. And then you can see your area report using the command report space area. So report space area is your area report of your design. So you can see what is your cell area and all, and what is your cell count, and what is your cell area. And you can see your net area as 0 because you are checking only your timing information. Because we are checking only the timing information of your design, that's why your net area will be 0. And then you can check your power report, report space power to check the power report of your design. So what is the leakage power of your design, and what is the dynamic power of your design, and what is the total power of your design. And then you can check your report gates option, so that you can see what are the list of gates available and what are the list of gates used in the design. So this is my gate report. from my slow.lib library. So AO cells are used of 24, and for all the 24 cells, the area is 181,656 micro square meter area. So similar way for all the list of cells, you can see for sequential cells, what is the area, and for logical cells, what is the area, and for inverter cells, what is the area. So that entire report you can see under your reports gates option. And then report underscore report space timing. So to check your timing report of your design. So to check your timing report of your design and what is the slack time it is taking. So my slack time it is taking is 994 picoseconds of time. So 994 picoseconds of time it is considering my timing to transfer the data. So in between these two pins, so these are the logical cells which are used for transferring the data of that particular cell. So that is your timing information of your design. And the next one is GUI show graphical user interface. So GUI represents graphical user interface of your design. So you will be getting your user interface. So on the left hand side, you can see hierarchy cell. So on the left hand side of your GUI, genus window, you can see the hierarchy cell. So select hierarchy cell, right click, select hierarchy cell, right click, schematic view and main view. So schematic view and main view. So schematic view and main view. So it will open you a design with your schematic window. So you can see how your pictorial representation of your gate level netlist file will be looking. So this is how your internal design structure will be looking after conversion of your logic into a gate level netlist file. So this is how your internal structures and this is how your internal logics have been built with the respective technology node of your design. And you can type history in your terminal so that you can see what are the commands you have executed till now in your terminal. So you can type history so that you can see what are the list of commands you have used in your terminal window. So this is your genus where you can perform your synthesis. And the next one is your DFT. For performing your design for testability, you need to invoke your genus tool in a legacy mode. So for invoking that, you can use the command genus space hyphen legacy underscore UI. So genus space hyphen legacy underscore UI. So invoking the genus tool in the legacy mode. So genus space hyphen legacy underscore UI. So that for performing the DFT, we need to generate some scripts for your DFT tool. So that generation of script will be done by using your legacy mode of your invoking of your genus tool. And from this, we will be generating that scripts and we will be loading that scripts into your modest tool flow for performing your design for testability. So similar way how we have loaded your library files. So the same way, and one more input file will be getting added, that is your setting of your scan style. So one more input, setting of your scan style information. So setting of your scan style information will be loaded under your design name. So after invoking your genus tool, so after invoking your genus tool in a legacy mode, you need to load your library files. The similar way how we have loaded for your synthesis with DFT, similar way we need to load your library files for your design. So genus space hyphen legacy underscore UI. 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 So after invoking the tool in the legacy mode, first we need to load the library files. So for loading that, set underscore ATTR. So for loading that, set underscore ATTR space. So for loading that library file, set underscore ATTR space. Set underscore ATTR space. Set underscore ATTR space lib underscore search underscore path. Set underscore ATTR space lib underscore search underscore path. Lib underscore search underscore path space your path of your library. So space path of your library. So slash home slash install slash foundry set underscore ATTR space lib underscore search underscore path. So you need to mention the path of your library. Slash home slash install slash foundry slash digital slash 90 nanometer slash dig slash lib. So that is loading of your library file path. And once again, invoking my terminal. And I'm invoking my genus tool in the legacy mode. Genus space legacy underscore UI. So for invoking my genus tool in the legacy mode, so after invoking the genus legacy tool, so first you need to load the library, set underscore ATTR space lib underscore search underscore path. And then we need to mention the path of the library slash home slash install slash foundry slash digital slash 90 nanometer slash dig slash lib. And then we need to load our library. Set underscore ATTR space library and slow.lib is my library file name. So I'm loading my library and then loading of your HDL file. Set underscore ATTR HDL search path. Set underscore ATTR HDL search path and then loading my HDL file also. So read underscore HDL and memory.v is my RTL file. So I'm loading my RTL file and elaborate and then loading of your HDC constraints file. So creation of your clock signal space hyphen name CLK space hyphen period, and that is your port connection. So get underscore ports of CLK. So loading of my clock input information. And then setting the clock transition time and setting the rise time of my clock signal. So 0.1 and get underscore clocks. So I'm mentioning my clock signal name. I'm mentioning my clock signal name of my design. Similar way, instead of rise time, I'm taking the forward set underscore clock underscore uncertainty. So I'm taking the 0.05 as a random value, and that is also the port connection. So at the external ports. So these are the 4 inputs which will be initially loading, and then we load of your design of set the style. So ATTR space DFT scan style. So DFT scan style, and we are using the multiplexers in the design. So instead of whatever the regular flip flops are available, we are converting into flip flops. So that we are in the multiplex scan style. Set underscore ATTR space DFT underscore prefix space DFT underscore setting scan style, and then defining the shift enable pin. So diff underscore shift underscore enable space hyphen name. So that is your enable pin and active. We are all putting your enable and to have that is a external option. So create a scope of showing of my enable pin and enabling of my then check the rule what are available and what are the asynchronous pins are available. So all that information will check under your check DFT rules. And then similar way, set underscore attribute sin generic. So we'll be performing your translation process. So sin underscore generic, perform your translation process and checking the HDL file, write underscore HDL, and then once again performing your mapping process, set underscore ATTR space sin underscore map underscore effort space medium, and then performing the mapping process by using the sin underscore map option, and then checking your file, write underscore HDL, and then performing your optimization process, sin underscore opt, and then performing your sin underscore opt to perform your optimization process, and then checking your HDL file, and then checking of your DFT route once again. So after performing the synthesis, it will check either any clock pins or any clock nets are missing in your design. So that is your checking of your DFT scan chain number. So define scan chain and the minimum number of scan chains. So defining the scan chain and defining the minimum number of scan chains in your design. So what the design it is available, the design to equal halves by using the DFT minimum number of scans. Set underscore attribute score. So DFT minimum number of scan chains, taking it to and your memory, so design space memory. So designs space memory, and we are defining the scan chain name. So define scan chain, and we are naming that scan chain name as top. And then for that input, we are taking it as scan in, and for the output of scan chain name as scan out, and these are all the external connections. So code that, and then cut the scan chains hyphen chains. So that will create your scan chains. After creating the scan chains, if there is any organization available, it will power optimization by using the sin underscore opt increment option. By using the opt viewer, and then you can report your scan chains. So report underscore scan chains. So report underscore scan chains. So it will report your scan chain information, how many available, so that individual scan chain number it will be reflecting. So total length is of 68. So we have taken into two scan chains. So 34 and 34 it is considering as a two scan chain information. And then we need to generate that netlist. So write underscore DFT underscore ATPG. So which will be generation of your test patterns of your design. So dot slash slow dot v for generation of your test patterns of your design. And then for generation of your netlist, write underscore HDL space greater than of dft.v, and for SDC file, write underscore SDC space dft.sdc, which is generated for the DFT process, and then write underscore scandef for loading your scandef file. So memory dot scandef file information, and then GUI show for seeing your pictorial representation of your design. So after performing your DFT, how your design will be looking. So select hierarchy cell in schematic view and in main view. So it will open you a pictorial representation of your design along with your scan input pins and output pins of your design. So at the bottom left corner, you can see your input pin names, and at bottom right corner, you can see your output pin names. So you can see this is my shift enable pin. This is my shift enable pin. So that is my shift enable pin. And along with, you can see your other pin names also. So whatever the scan in and scan out pins you have considered, so all the pins will be reflecting in your design. So all the pins will be reflecting in your design. So D input, write enable and all. And along with that, you can see your scan in and scan out pins also of your design. So that is your synthesis with DFT. So that is your synthesis with DFT. And now you can invoke your modus tool. So now you can invoke your modus tool. So for invoking the modus tool, you can use the tool name. So modus space. So modus space hyphen legacy. So modus space hyphen legacy underscore GUI. So modus space hyphen legacy underscore GUI for invoking your modus tool. So modus space hyphen legacy underscore GUI. So if you are working on any testing tool, you need to invoke that testing tool in a legacy mode only. So you need to invoke that testing tool in a legacy mode itself. So model space hyphen legacy hyphen for in your graph user interface. So underscore GUI reference graphical user interface. So model space hyphen legacy underscore GUI. So legacy underscore GUI for reflecting your GUI show under your modest tool. So for performing that modest tool first we'll be building the model. So first we'll be building the model. First we'll be building the model of your design. First we'll be building the model. So this is the modest tool flow which it will be happening. So first we'll be creating a build model. So first we'll be creating a build model, and then we'll be moving to your build model, and then we'll be creating a model, and after that we'll be verifying that model, and we'll be creating a fault models in the design, and after creating the fault model we'll be implementing that faults into your test pattern generation. So that is how your modest tool flow will be taking care. So after invoking your modest tool, you can go to file, new option. So you can go to file, new option. Sorry. You can go to file, new option. So in that you will be getting your working directory. You will be getting your new project window. So in that you will be getting your working directory. So from that working directory, you can select you can select your browser. So you can select your browse option, and you can select your test scripts folder. You can select your test scripts folder, and you can click on OK, and you can design your design name. So we are working on the memory design. So my design name is memory, and I am clicking it on OK. So my work clip will be created under your under the column. So similar way, first we will be building the model, and then we will be testing that model, and we will be creating a fault model, and then we are creating the ATPGs and writing the vectors. The same thing will be following for your any design procedure. So for that, you can go to verification, build a model. So you can go to verification, build a model, and model. You can select your netlist file name. So you can select your netlist.v file name, and you can select your cell name. So we are taking the cell name as memory, and you can click on setup option. So it will open you a library file window. So where you need to browse your .v file. So where you need to browse your .v file. So /home/install/foundry digital 90 nanometer dig and vlog. So Verilog file of your design. You need to select your slow.v file because we have used slow.lib library file for our design. So you can select slow.v file, update project. So it will click, you can click on run option. So that will show you your fault model creation of your design. And at the bottom, it will be showing you the log window and how that has been created. So you can see under the build model what is happened. So you can switch to task next to methodology on the left hand side. You can switch to task and you can select build model, and under that build model you can select log option. So either you can see the log report over in the bottom model window, or you can see at the bottom side also. So it will be creating a two models. The first one is hierarchy model and the other one is flattened model design. So for hierarchy model, how many blocks are taking? You can see the summary report of the design. So for creating the hierarchy model, how many blocks are considering? And for creating the flattened model, how many blocks are considering? The detailed summary report will be available under your building the model. So after building the model, we need to verify that. So you can go to verification, build model and test mode. You can go to verification, build model and test mode. So you can define your test mode name as full scan. So you can define your test mode name as full scan, and you can browse your .pin assignment file, and you can browse your .pin assignment file, and you can click on open, and you can click on run. So that will run your test model condition, and that will run your test model condition. So my test model condition is showing some error message because I need to give it as full scan. It is showing some other name. So that's why we'll recreate it once again the model. So build, verification, build model and the test mode name. So here it should be it as full scan. So it should need to take it as full scan and run option. So it will create your test module name as test mode as full scan. And you can see that log report, how many are in active stage of your design, how many are in active stage and how many are in inactive stage. And along with that, how many, what are the pins it is considering. So all that report will be taken care under your test mode analysis of your design. And the third one, creation of your fault model. You can go to verification. So you can go to verification. You can go to verification, build model, fault model option. You can go to verification, build model, build fault model option, and you can disable the dynamic faults option, and you can click on run option so that you can see how many faults are available, how many faults are possible in the design to create. So building the fault models, you can see how much fault model has been created, and that fault model report has been saved in your TB data of fault model and fault status reports. So you can, if you scroll it up, you can see how many faults are possible for the memory design. So total faults or possibilities 2412 faults are possible for the design. So that is creation of your fault models of your design. And then next one is reporting the structures. So you can go to report. So you can go to report test structures option. So you can go to report test structures option. So select your test mode name. So select your test mode name and click on run option. So that will report your test structures. So that will report your test structures. So how many test structures are possible and how many are available. So that reporting the test structures information, it will be generated. And next one, we need to verify the test structures. So you can go to verification. So you can go to verification, verify test structures. So you can go to verification, verify test structures. And you can select your test mode name as full scan, and you can click on run, and you can click on run. So that will run your that will verify your test structures of your design. So that will verify your test structures of your design. And the next one, creation of your test patterns. So you can go to ATPG. So ATPG represents automatic test pattern generation. So ATPG, create test, specify static test. So you can go to ATPG, create test, specify static test, and scan chain information. So define your define your test mode name as full scan. So first we'll create the test patterns for the scan cells. So taking it as scan and run. So creating the test structures for your scan cells, then creating the test structures for your logical cells also. So once again, you can go to ATPG. Create test, specify static test, and logic. So you will be getting your test structure name. Define your test mode name as full scan and your element name as logic. So generation of your test patterns for your logical cells also. So that is your creation of your test patterns for your logical cells also in your design. And then writing the vectors, you can go to ATPG. So you can go to ATPG, write vectors option. So you can go to ATPG, write vectors option, and select your test mode name as full scan, and select uncommitted vectors. So first generate the test vectors for logic, and first generate the right vectors for logic cells, and then generate the vectors for your cells also. So ATPG write vectors. So ATPG write vectors and generate the structure write vectors for your scan cells also, and run. So that reports will be saved in your current working folder of your testing results of your design. And then that is your modest tool flow. So that reports will be saved in your current working folder. You can go back to that particular folder as memory. So in memory, you are having a folder as test results. So in that test results folder, you will be having the TB data. So in that TB data, where you will be getting your fault structure information. So you can see the fault model, and you can see the fault status, and along with that you can see the test mode and test status also. And if you go back, you can see your test results. So in that test results, you can go to Verilog. So in this Verilog, you can find the Verilog of scan cells and the Verilog of scan logic cells also. So each and every information will be available in your current working folder. So that is your entire modest tool flow, and the remaining the physical implementation flow, we'll be seeing that in the afternoon session. So we'll be seeing that in your afternoon session. So if you have any doubt, you can let me know, so that I'll be helping you out. Hello. So that is your till DFT part. So if you are having any doubts till DFT, you can unmute yourself and you can ask so that I'll help you out.
Participants, is there any queries? Please unmute yourself and ask your queries to our resource person. Participants, is there any queries? Please unmute your mic yourself and ask your doubt or any queries to our resource person, or you can put your queries to our chat box. Sir, I think there is no more queries.
Sure, sir.
Okay.
Yeah, thank you. Thank you.
Okay, thank you, sir. You can again join at 2 p.m., sir.
Okay, sir.
Okay, thank you, sir. Participants, the day 3 session on feedback is posted in the chat box. While filling the feedback form, please select your corresponding FTP ID respectively.
Dear participants, morning session is over. So again, you can join afternoon session at 2 p.m. So attendance and feedback link are posted in our chat box. So kindly fill it